Many of our building materials are already carbon-based, right? They're already using carbon. It's not necessarily carbon that we've pulled out of the atmosphere, but it is carbon. The idea, though, is that if we're able to get equivalent or better performance out of these materials and store atmospheric CO2 in them, we could have this really net benefit of leveraging this huge mass of materials that is available to us.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Podker. Concrete is the most widely used construction material in the world. It is the backbone of what is called the built environment, a crucial ingredient for housing and infrastructure development. Advances in materials science and processing can enhance the long-term durability of many building materials, including concrete, enabling significant economic and societal benefits. We're joined by Sabbie Miller, an associate professor in the Department of Civil and Environmental Engineering at the University of California, Davis. Her research is dedicated to advancing the built environment through the development and optimization of infrastructure materials. Professor Miller, thank you for joining us today.
Thank you so much for having me.
So I want to start with kind of defining one of the terms that's kind of key to what we're going to be talking about today. What is the built environment?
So folks do use the built environment in a couple of different ways, but typically what they're referring to is basically all of our buildings, so houses, apartment buildings, hospitals, school buildings, offices, as well as all of our infrastructure systems and roadways, so sewers and highways and all of those things together are the environment that we as humans are building for ourselves. And so it's often referred to as the built environment.
The most kind of common material is concrete. So we're going to be talking about a lot of concrete today. I want to start with the manufacturing process. What are kind of the problems with manufacturing currently?
So there's a couple of things to think about with concrete. Yes, it is our most consumed building material worldwide. It's actually a composite material. So it's made out of cement, water, and crushed rocks, which we refer to as aggregates. So sometimes cement and concrete are used as synonyms, but in reality, cement is this powder that reacts with water and holds together rocks to make this synthetic rock that we refer to as concrete. And some of the manufacturing challenges associated with the production of concrete are actually tied to that cement. So when we're worried about things like the environmental burdens for concrete, it's a function of a couple of things. One, we use a heck of a lot of this material. Right. So whenever you use a lot of something, its impacts scale accordingly. And then on top of that, to get the reactions to take place, we require thermal energy. And so then we also have energy-derived emissions tied to the production of cement. So when we're talking about the impacts of concrete, oftentimes the impacts are things tied to cement that we're worried about.
We hear about a lot of buildings when they get torn down going straight to the landfill. Can we crush them and reuse them as an aggregate, let's say, in any new concrete? Or is there issues with that carbon cycle and the bits of the cement you just explained chemically?
It's a yes and no response to that. We can crush our concrete and get some benefits out of that product. The other thing, though, that we end up seeing from our crushed concrete is exactly as you mentioned, it's made out of hydrated cement and aggregates, which means it's not the same performance as the aggregates alone. It's now got this like caked on hydrated cement stuck on the material. So it doesn't have the same performance as our normal aggregates that we would normally crush and use in our concrete. In California, where I am, I know that our Department of Transportation actually uses the concrete from the roadways that we have, crushes it up and uses it as road base for the new roadway that they're about to put in because it has great performance characteristics for that. So we can use it in some ways, but not in all ways.
So thinking about it, potentially reusing it for like structural purposes, it might have a weaker fracture value or something.
Yeah, the paste itself can have certain performance characteristics associated with it, the cement that's interacted with the water and created this kind of binder material. The aggregate's going to have certain performance. And then there's what's referred to as the interfacial transition zone, this region where the cement is actually bound onto the aggregates that has its own microstructure associated with it. So yes, we end up with potentially different fracture performance associated with that. Other types of durability issues can also be tied to having this effectively like a three-phase material as opposed to just the aggregate. So yeah, there's a couple of different issues that could happen that might hinder use in certain applications.
Awesome. So the paper that I read that kind of brought your work to my attention is looking at using building materials for carbon storage. So how might that be possible?
So many of our building materials are already carbon-based, right? They're already using carbon. It's not necessarily carbon that we've pulled out of the atmosphere, but it is carbon. So part of what could happen is if we're able to re-engineer those materials such that the carbon that's in the material is coming from a direct air capture system where we're basically pulling atmospheric CO2, concentrating it, and then using it in those materials, then we could potentially store them for a really long time in the built environment. The other way we could do that is capturing flue gas, so carbon capture, actually trying to capture the CO2 as it's coming out of industrial processes, energy generation processes, and then again concentrating it, using it in our built environment as the carbon source, and potentially even having the materials themselves directly capture carbon dioxide from the atmosphere. This happens a little bit more with our biogenic materials, materials that are living organisms like our photosynthetic materials. So if they're able to already interact with the atmosphere through photosynthesis, they can pull in carbon, and then we could use that material as something in the built environment. So there's a couple of different ways to get that carbon stored in our materials, but it depends on the material that you're talking about.
I know part of the study you were looking at the effectiveness of different kinds of blocks like concrete, brick, asphalt, plastics, woods. Can you talk a little bit about the effectiveness of these different forms?
Yes. So depending on the amount of carbon that you could put in any material, you're going to have a certain degree of potential effectiveness based on the carbon content, right? So this is a very high level of carbon for this material. So in theory, we could store more carbon in this material on a weight basis. The other thing, though, that we found was a much larger driver than that component was how much of this material do you plan on using? So even if you're getting less carbon stored in the material, but you could scale it to an enormous quantity, like something like concrete, then potentially you have this huge body that could store carbon dioxide as long as you're getting desired performance out of the material. So if the material has any loss in strength or the ability to place it during construction, or if it fails earlier than our conventional material, then you could end up not seeing these benefits. So the performance of the material is always priority. The idea, though, is that if we're able to get equivalent or better performance out of these materials and store atmospheric CO2 in them, we could have this really net benefit of leveraging this huge mass of materials that is available to us.
Now, one of those materials that I was curious to ask you about is bioplastics, because we hear about plastic and think about it being like more of a manufactured toxic thing. What is a bioplastic?
So bioplastics are plastics where the carbon in the long chain molecule that makes up our plastics is coming from a bioresource as opposed to a petroleum-based resource. So the vast majority of our plastics that we interact with are coming from petroleum-based resources. That's where their carbon is coming from. But instead, if we're able to use things like food waste, not priority food, not food that we would otherwise eat, but waste that we would have otherwise disposed of, or residues from different agricultural or forestry practices. So a biomass that we otherwise need to get rid of isn't going to be a priority for something else in terms of its utilization. If we could use those as the source of carbon, then we could potentially reduce our dependency on petroleum and leverage a bioresource that has pulled CO2 out of the atmosphere. We might have access to it a little bit more locally because of the ability to use different types of bioresources. So there's a couple of different strategies that one could use, basically leveraging that source of carbon to replace our more petroleum-based carbons in those materials.
Can we put a nose on some of the side products? Would this be like, say, in the corn industry, like the husks or something that probably don't have a lot of use otherwise, but could potentially be used in this way?
Exactly. So it's not the kernels that we would otherwise want to eat, but yes, the husks, straw, leaves, all of those sorts of things that would otherwise be cultivated, but not necessarily have as much value. Now, I will note that we don't want to take all of that off of the farmland because farmers actually do need some of those nutrients to go back into the soil. But if it is already being removed, then that type of biomass can be really valuable for products like bioplastic.
Interesting. Now, one of the other things I wanted to ask you about was geopolymers and their use in kind of alternate cements. Can you talk a little bit about what these things are?
Yeah, so there's a class of alternate cements that are referred to as alkali activated materials. Basically, it's leveraging two main components, a aluminosilicate solid precursor, so something that has a lot of alumina and silica in an amorphous state, kind of like a chaotic, crazy state, not very well aligned in a crystalline state, along with alkali activators. When those are combined appropriately, then we can actually create something that acts like a binding material, just like our regular conventional cement with water. So we're basically able to replace our normally highest CO2 component of concrete with something that doesn't require the same decarbonation of limestone, nor does it require that same energy demand that our conventional cement requires. So if we're able to replace that, there's this idea that potentially we could reduce a lot of the impacts that we would normally associate with our cement and our concrete. Geopolymers are a subclass of alkali activated materials. So they happen to be one of the ones that's really well studied, but it's in that class of materials that have these two key components associated with them. And there's a lot of work going on right now trying to understand where can we get those aluminosilicate solid precursors, where can we get those alkaline resources such that they are globally available and they themselves don't have high impact. Because if we have to process them a lot, then we could kind of counter our own benefits.
Right. That was going to be my next question, like trying to think about that for people that aren't too specific about the chemistry there. Can you talk about something that might be an example of what that ingredient would be?
Yes. So our most commonly used alkali activators would be things like sodium silicates and sodium hydroxide. We use those kind of alkali resources in a bunch of other applications as well. In terms of the solid precursors, a lot of work is looking at things like the utilization of coal fly ash and ground granulated blast furnace slag, which we already use in the cement and concrete industry. Coal fly ash is actually, it's exactly what it sounds like. So we use coal for the generation of electricity in many parts of the world. And those ashes actually have really desirable characteristics associated with them for this kind of perspective of utilization of aluminosilicates. They have great characteristics for reactivity, a nice disordered structure, et cetera. There's also a bunch of other resources, though, as well. So a lot of our agricultural products have a wee bit of mineral in the biomass itself. So again, not the food, but those residues like the corn husks, like rice straw, et cetera. When we use those biomass products, it's predominantly carbon again, but if we tried to recover energy from the biomass through something like oxidation, et cetera, we could then take the mineral compound that's left over as an ash form and use it as a solid precursor for the formation of alkali activated materials. The industrial byproducts, the agricultural residues, forestry residues, if we're able to really utilize those properly, we can actually start to make a pretty notable dent in the material.
So as you develop these kind of different materials, is there kind of trouble getting industry to buy in with using byproducts and using different kind of techniques to get at these things they've traditionally used with limestone and Portland cement?
Engineers are very focused on performance for good reason. We want to create products that work. That is our main goal. And a little bit of tweaking to make them work even better is also one of our big goals. That said, civil engineers tend to be on the even more risk-averse side than conventional engineers. We really try to make sure that things are working properly. Reason for that being things like life safety issues. You don't want to hop on a bridge and have it collapse or have a building collapse. We really want to make sure our systems are working incredibly well. And we use a few things to make sure that we are reducing risk. A lot of probabilistic modeling, trying to understand exposure conditions, trying to understand how we could best design these systems to reduce likelihood of any type of failure associated with them. And also our historic knowledge. I put this material in here 20 years ago, it's still doing great. I'm comfortable using it again. That ends up being a really strong driver. Also validation from other parties. That other person used this material. It was really successful. That means I have a higher likelihood of it being successful. As you can imagine, incredibly valuable. We don't want to remove this idea of minimizing risk. We want to make sure that safety and performance are number one always. But if you come up with a brand new material, there's a little bit of aversion of using it because this kind of knowledge of how it's going to perform and comfort associated with its use isn't necessarily there. So we end up seeing that civil engineers are a little bit less likely to rapidly adopt novel materials because we need those materials to perform well so that we make safe structures, and we need them to perform well for a long time. They have to keep going for decades. because there's a lot of work going on right now trying to understand how we improve adoption of alternative materials. How do we make sure that we have the proper validation so that we're removing that risk from the practicing engineer? They should not be the one who has to take that on. Do we change our overall insurance structures so that there's more comfort trying to use some of these materials? Should we change how we're structuring kind of later stage testing so we're better understanding durability? Is there something that we do in order to understand any type of barrier for actually placing the material? All of that is a really active area of research.
Everyone's really excited about AI right now. Are you guys using AI in your lab as part of any of that kind of analysis process?
Yes. It's a tool. Engineers love tools. So yes, we do use AI, machine learning algorithms in order to kind of help predict certain things. So rather than conducting test over test over test so that we get a battery of information, there are researchers around the world who are collecting fantastic information. So yes, we are leveraging things like AI in order to use many different data sets that might not all have been performed in the exact same way, such that we can still predict robustly the likelihood of material performance. And we're also leveraging it to inform things where we have otherwise data poor environments. So quantifying environmental impacts, for example, is a very data intensive field. And sometimes we have gaps in some of the inputs that are necessary, but we can leverage AI to fill in some of those gaps, still with a bit of uncertainty, but better than our just guessing. And then also we have the utilization of AI for some of overcoming barriers for adoption, trying to understand, okay, we have very limited data for these particular types of performance metrics. How can we predict what we would expect behavior to be, or predict what tests we should be doing in order to fill in some knowledge gaps in that realm as well?
I also wanted to ask you about NSF support. What difference has, say, your career award made for you?
NSF support has been the best support that I've had as a career. I realize that kind of sounds like I'm pandering. At the same time, though, NSF support actually allows us to do this kind of more foundational understanding type research as opposed to more applied with a high likelihood of success. We have those grants as well, right, where we kind of know what's going to happen, but we need to validate it, or we're just filling in one nugget of a particular field in order to make sure it's robust. Those more applied bodies of work are fantastic. But NSF has facilitated my group actually looking at new areas where we don't have a solid understanding of how this could pan out, or where we should be focusing our attention. So it has facilitated work like the work that we've been discussing about what would potentially store carbon and where could we get the biggest bang for our buck in terms of trying to utilize carbon in the built environment. We end up seeing that NSF has actually been incredibly valuable in trying to support that type of really groundbreaking work.
I want to ask you another left field question and put on a speculative hat for a second and think about where materials might be. Where would you like to see cements or concretes in, say, 75 years?
I'm a bit of an optimist, so I would like to see them having higher performance characteristics so that we don't need quite as much of the material. Obviously, we can't get rid of all of it because there's only so much you can cut back and still get the right amount of roadways, buildings, et cetera. But higher performance characteristics out of the material. I would love to see the material obviously at least at net zero emissions associated with it, but also ideally something that could be a net uptake, a net storage system for our environment. And I would love to see more on circularity of resources tied to our use of concrete. So just like you mentioned, this kind of use of concrete, crushing it and getting to use it again, we haven't been big on resource circularity in general, not, calling out concrete, but in general, humans have been a little bit more linear in the life cycle of our materials. We'll extract, we'll process, we'll use, we'll dispose. I'm really excited about the kind of concept of how we can start to re-engineer things so that when we're taking it out of use, let's use the resources again such that they're circulating through our economy. Perhaps not straight into the same class of materials or the same class of products if we are losing performance, but how can we start to reuse those resources so that we don't have to keep extracting resources, which would facilitate our potentially being able to continue building in a very robust way.
So for the very last question today, I want to ask you about what's next in your work.
We actually are continuing doing work in circularity because I find it so exciting. Also because there's some issues tied to resource consumption and localized scarcity. So we might end up having areas around the planet where we have plenty of the material globally, but in this particular area, we don't have enough access to it. And now we've got to import it from other areas, which can cause a variety of different stressors on the environment, as well as other types of stressors. So trying to better leverage the resources that we're taking out of use, that circularity is something that we're incredibly excited about in the group. We're also looking at paired material and energy systems. So humans are fans of energy, electricity in particular, and trying to understand, okay, if we are going to need to continue to produce electricity, how can we make sure that we have access to that electricity while also creating co-products that benefit other types of systems, such as materials production? How can we pair those together such that we're able to generate energy and create a net storage mechanism tied to that energy generation, so we're getting the benefit of our energy resource, but also removing CO2 from the atmosphere or undoing air pollutant issues that we've sent into the atmosphere, trying to integrate those together. And then, of course, continuing work on decarbonizing materials production and creating net uptake, net storage systems. Those are areas that I'm incredibly excited about.
Special thanks to Sabbie Miller for the Discovery Files. I'm Nate Podker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.